stop us from removing the tentacles of the Chi-Com/Big Tech banking combine emergency situation. I have been chosen for destruction because I brought you this information and have been battering, ramming it out as much as I can. They want to double use me as they always do in any complex system of mathematical deception where every angle of my good is turned against us. So they take what I've said, being sincere, build me into an insincere person in the straw man. I'm a person that cares about life and children and is against these wars. And so they make me a murderer of children. And then they build me into this lie to then set the distraction while they're actually censoring all of you to make a debate about Alex Jones. So even if I didn't sell out to them, they now use me as an archetype to serve them by being the main distraction. I have now been captured by the enemy in the information warfare fulcrum and is being used against you. Only your full understanding of this TV will break you free from this paradigm. I have given you the transmission. Now break free.
I have sworn upon the altar of God eternal hostility against every form of tyranny over the mind of man. Thomas Jefferson. If you are receiving this transmission, you are the resistance.
Ladies and gentlemen, thank you for joining us on this Friday, February 8th, 2019 broadcast. I am not going to be able to be on air right now because we're working on such a big, important story. I'm going to have to air some promos when we come back because I need to get our ducks in a row. Last night we got blindsided by some of the raw footage being released by Sinclair.
Manifest in simple analytic properties of the amplitudes. At tree level, they only have poles. At loop level, you have cuts that correspond to internal loop momenta going on shell. And all of that is totally manifest in Feynman diagrams. And it's totally manifest at the expense of making a simple process like 2 to 3 gluon scattering look like that. 25 pages of horrible algebra. If you open up Peskin and Schroeder and copy out the Feynman rules and do the calculation, that's what you get. And yet the actual answer is something that's just one term, the famous Park-Taylor amplitude, whose 30th anniversary was earlier this year. So now, those amplitudes are simple. People saw that already back in the 80s. Back then it wasn't clear that it was a tip of a very big iceberg. Today it's clear it's a tip of a very big iceberg. And most of the iceberg that's been seen has been in the context of planar n equals 4 super Yang-Mills. I think best named the hydrogen atom more than the harmonic oscillator of the 21st century. For example, there's this famous hidden dual conformal symmetry of the theory that's actually there in any number of dimensions. So it's ironic, in any number of dimensions there's this hidden symmetry, and only in 4 dimensions is there the obvious conformal symmetry, at least at low enough loop orders for this statement, at high enough dimensions. And together they form in 4 dimensions this famous infinite dimensional Yangian symmetry, again in the planar limit of the theory, which is completely invisible in the Lagrangian. So the amplitudes are simple, they have hidden infinite dimensional symmetries. None of that is made manifest in the usual way of thinking about field theory. And why? It's because there is a heavy price to making locality and unitarity manifest. Even for simple theories, scalar theories, anything, there is lots of redundancy. There's the redundancy of field redefinitions, and then when we have massless particles with spin, we have gauge redundancies in order to help us describe in a local way the dynamics of two helicities for massless spin 1 particles, let's say, in terms of fields, things like polarization vectors and so on. We need to say that there's a whole equivalence class of polarization vectors that differ by translations parallel to the momentum in order to knock down the degrees of freedom from the 4 of the polarization vectors. So the tendency to have so much insane new physics at the LHC that it was going to be very difficult to disentangle it all. And so we had to come up with all sorts of new and interesting methods to do it. And anyway, so we're having a lot of fun with it. And at this meeting, I talked about something that it's not obvious aspect of it, which this is just some way to go about modeling things at the LHC for phenomenological purposes and so on. Motivation is to try to describe the physics. What I presented was it's just not the case in this business, and I think it's actually rather interesting. Of course, the real world is not Euclidean, but in thinking about amplitudes, you can and copy it. So to see, it's very simple to see in 4 dimensions, where we have these famous spinor helicity variables for writing the form momentum of a particle. And the important point about these variables conceptually is that they make the action of the little group on the amplitudes manifest. So scattering amplitudes are not functions of, they're not Lorentz tensors. They have to transform when you transform the momenta with the Lorentz transformation. They have to pick up a little group transformation on the helicity labels, and that's non-trivial. We pretend that such a thing as polarization vectors exist that are like a bifundamental between the Lorentz group and the little group, and they don't actually exist. They only exist in these gauge-dependent equivalence classes, and that's the origin of the complexity. So what you'd like to do is find variables on which the little group acts nicely, directly. And that's what these spinor helicity variables are. See, the whole point is that here's a null momentum, and here's something you can do to rephase or rescale lambda and lambda tilde by opposite amounts that leaves the p invariant, and that's precisely the action of the little group. Now, furthermore, the kinematics of momentum conservation is especially simple for 3 particles, and by familiar arguments, you can fully determine what the 3-particle amplitude is once you specify the helicities with 2 different choices depending on whether some of these helicities is positive or negative. And then you can ask a simple question. The 3-particle amplitudes are fixed up to an overall constant. Now you can assume that there's some underlying theory of the weak coupling, so that you're talking about something like a tree approximation. So the amplitude is only going to have poles. So we're restricting ourselves to theories like that. But then the requirement of unitarity is just that the 4-particle amplitude should factorize correctly. You have to somehow write down a 4-particle amplitude. This thing can now depend on S, T, and U, as well as just helicity information. But you have to make sure that as, let's say, S goes to 0, it factorizes correctly in the product of the 3-particle amplitudes. Okay, now you might think this is really easy to do. So let's say I have a phi cube theory. It's completely trivial to build a 4-particle amplitude that does this because, let's say I want to match residues somewhere. You would first go there and see what the residue is. So the amplitude is just a constant times a constant for the 3-particle case. You get g times g, it's g squared, and say, I know how I'm going to match the residues. I'll just multiply by 1 over s minus m squared, and I sum over the different channels. Okay? So that seems to be trivial. Once you know the 3-particle amplitudes, you figure out the residues, you dress with the you dress with the pole factors that you had stripped off, and you're done. But it's non-trivial when we have massless particles with spin for the following very simple reason. If you go compute the residue in the S channel, let's say for this helicity configuration, I'm assuming these are all particles of a single spin S, a massless particle with a single spin S, you discover that you can compute the residue, but it's not local. The residue in the S channel is not local. It has a 1 over T in it. See, so that's tricky now. So now it's not obvious. Now you might want to take that guy and shove a 1 over S in front of it, but now it's not obvious it's going to give you the right answer because it has a T in it. It's not obvious it's going to give you a right answer when you go to the other channel. In this case, when S equals 1 and S equals 2, well, in this case there's a T, And you can do it because if you actually just multiply this whole thing by 1 over st, thankfully there's also a pole in the t channel that's supposed to be there, and it's exactly right. Okay? Now this looks a little scarier. There's a 1 over t squared if you do it for spin 2. That might make it look like you'd have to have double poles in the denominator, and that's wrong. But no, it's okay because it's gravity. That t squared could really be a t times u when s equals 0. And the full amplitude is allowed to have a pole in s, and a pole in t, and a pole in u. Okay? So that's why we can now directly write down the 4-particle amplitude. We just take the residue. We say it had to be s times, it has to be t times u, then we multiply by 1 over s, and everything works. Okay? But you see that it's not trivial because of the poles in the other channels. And this is, I think, the most invariant way of seeing the tension between locality and unitarity for massless particles with spin, even more invariant than talking about the need for gauge redundancy with a Lagrangian, because it's reflected directly in the structure of what the amplitude is. If I give you the amplitude for phi cube theory, it looks like a sum over the s and t and u channels. But if I give you the amplitude for this is gravity, it can simply not be written as a sum over different channels, okay, in a Lorentz invariant way. So, and of course we can write it as a sum of channels in a Lorentz non-invariant way. That would be like doing a calculation of a light cone gauge or something like that. Okay, but that's just, we see precisely this tension between Lorentz invariance, locality, and unitarity. By the way, this is also the one-line explanation for why there's no such thing as maximal off-shell superspace. Okay? If you do exactly the same computation in a maximally supersymmetric theory, this numerator just turns into a big supersymmetric delta function. And so you imagine if there was a theory with had maximal off-shell superspace, then you would be able to compute Feynman diagrams in that theory and get an expression with a sum over s and t and u channels, and you just can't do it. Every single term would have to have this delta 16q in it, and once you strip that off, it's simply not a sum of a function of st and u. So this tension between Lorentz invariance and unitarity for massless particles is related to the tension between supersymmetry and locality that we all know and complain about as we make supersymmetric theories with more and more supersymmetry. They're harder and harder to describe in Lagrangian language, okay? And it's very closely related to the tension, to the need for gauge redundancy when we describe these things with Lagrangians. All right, now we can keep going. And this is an exercise that's possible to do very systematically. It's been done in a number of nice ways in the past couple of years. The presence of massless higher spin particles from these considerations can be just ruled out by the presence of gravity or Yang-Mills. I'll just give an example of charged massless particles, charged under a photon, of spin s. You do the same exercise, you compute the residue in the s channel, and now you find that it has a 1 over u to the 2s minus 1 in front of it. And the second s is 3/2 or above, now you're dead. There's nothing you can do. You're forced to have a double pole, multiple pole in the denominator, and it's just impossible. And you can do an exercise where you conclude that the only possible consistent 4-point amplitudes that you can have correspond to theories that have particles that spin 0, 1/2, 1, 3/2, and 2. 2 has got to be unique. You can only have 8 of these guys. That's Yang-Mills, all the theories that we know and love. Just to give you a small example, how do you discover supersymmetry like this? Okay, so you put in massless particles of spin 3/2. That's no problem. They interact with gravity. It's no problem. But now let's say you add one scalar to the theory for fun. Now you look at the amplitude for the spin 3/2 scalar scattering, and you discover that when you look at the t-channel residue, it has an s-channel pole. Okay, so the only way it can possibly be consistent is that if there are a particle in the s channel that could make that up, and that's the superpartner of the scalar. So all of these things come out in a very, very simple way. All right, so anyway, so that's so that's just that 4 particles is very simple, but in a sense, a lot of the modern S-matrix program is trying to go beyond this to talk about things, more particles, more loops, and so on. And the philosophy is to exploit locality and unitarity, just like we did in this very simple example, to determine the amplitude. So with more sophisticated ideas, things like generalized unitarity, BCFW recursion relations, leading singularities, and so on. But there's a converse philosophy that I think is also interesting to a take, which is the fact that making these things manifest obscures all these marvelous structures, suggests that we should look for a new picture for what the amplitudes really are, where the space-time and Hilbert space don't appear. And if we can find such a picture, then we can understand how locality and unitarity might emerge as derived notions from something else. And this is a very concrete setup where you know exactly what these things mean. You have functions you have to match, they have to have the right singularity properties and so on. And so you can either use these principles to determine them, or you could look for some other structure that generates them in a different way. Now, I want to just say a few things about this last point, that we might look for something where locality and unitarity sort of emerge from other principles. I just want to say a few general things about it. Of course, it's a very, very speculative idea. But I first got excited about this idea by a talk that Nathi gave at the Solvay meeting back in 2005. There he is. Of course, everyone talks about emergent space, emergent space from quantum mechanics, and Nathi made the point forcefully that, of course, we have to care about emergent space-time, and if time is emergent, it's not obvious that quantum mechanics has got to be just left alone, that it's just going to commute and go along with the ride. This is, I'm sure other people have said it before, but it was said very clearly and very forcefully. It made a very big impression on me back then. And just to sort of contrast what the hope or the idea is here is that instead of imagining that there's quantum mechanics and gives us emergent space, and of course we believe this happens, and we'd like to understand more and better how it happens. Here it's something much vaguer at the moment, but the idea that there's something else, and out of it comes both quantum mechanics and not just space, but space-time, and that they have to emerge together, somehow joined inexorably. I just want to give a couple of, these are some general remarks, but I want to just give a couple of broad motivations for this, because I think there are some big reasons to expect it and some little circumstantial hints to expect it. One, of course, is we all know that we eventually run out of precise quantum observables in various questions that we like to think about, in following observers into black holes, accelerating cosmologies, and so on. And so we look for quantum mechanical observables, and we eventually run out of them. And so we don't know what we're supposed to be talking about. So there's at least a place where it's conceivable there might be some kind of extension of quantum mechanics needed. There's something else which certainly bugs me, I'm sure bugs many, many people, is that there's this huge tension between the two revolutions of the 1990s. On the one hand, we got this idea, especially in the flat space limit, that there's this one unique theory and they're all dual to each other, and we can have all these different possible backgrounds as solutions of one theory. That's one picture. Then we have the ADS-CFT picture, where more or less any old quantum system is dual to an ADS theory in the bulk, and these two things just don't feel the same as each other, right? So it doesn't seem crazy that there might be some more bulk-flavored picture of the physics. And since there's no local observables, quantum local observables, maybe that more bulk-flavored picture of the physics will be more relaxed about quantum mechanics. It's an absolutely wild speculation, but it at least motivates you to look for this. Motivates you to look for things where it's not just the Hilbert space which is dominant, but that somehow both sets of concepts should come out together. Now, I think there's other more elementary circumstantial clues. One is that our best pictures of field theory don't start in 3+1 dimensions. For example, most standardly, we start in Euclidean space, where the objects that we talk about don't have the interpretation of amplitudes, nor is there any time. And then we do an analytic continuation, and the second time emerges, they become probabilistic. They have a quantum interpretation at the same moment. And there's some analogous things that's being seen in the context of amplitudes, where you start from 2+2 signature. And there's the other sort of basic fact that local space-time and quantum mechanics somehow buttress each other. If there was no quantum mechanics, we could have imagined that Lorentz invariance was an approximate long-distance symmetry, just like waves on a rope. But it's quantum fluctuation that makes it very, very hard to get Lorentz invariance to come out as an approximate symmetry. If it wasn't for Lorentz invariance and causality, you could imagine making stupid local hidden variable models for quantum mechanics. It's relativity that makes quantum mechanics more rigid. All right, and the final thing, most closely tied to the subject of the talk, is that the locality and unitarity of scattering amplitudes are reflected in sort of one and the same property of these objects. Just the singularities of the amplitudes naturally tie both locality and unitarity together. Okay, so now I'm going to, here are the two things that I want to talk about, depending on how I'm doing for time. We may not cover them equally. But the two topics I want to talk about are first, the final answer to Nutti's question. So he asked me back then if we were talking about, with these on-shell effective theories for collider physics, if we wanted to eliminate virtual particles there. And I said, of course not. And now I want to tell you exactly how we can do that, not just for, theories with massless particles, but just normal standard model processes. What are the S-matrix rules, in fact, in general, for any masses and any spins? And this is work in progress with Yutin Huang and Chuchu Huang. And it's motivated by trying to better understand four-particle scattering amplitudes for general string states in string theory, but I won't talk about that part. I'll just tell you about how to go about thinking about the S-matrix for general mass and spin. So that's in the S-matrix program direction, and in the opposite direction of trying to find a different set of questions that the amplitudes are answering. That's something that I've been working on for many years. And there's interesting structures in combinatorics and algebraic geometry that have shown up. And the I think most invariant way we've found so far of thinking about these things is something that's being done in collaboration with Hugh Thomas, a mathematician at the University of Montreal, and Yaroslav Trenka, which tells us to, first of all, think about scattering amplitudes as differential forms, and secondly, they're seen that they're actually completely specified by a pattern of string bits, pluses and minuses. There's, in a very specific sense, they're a binary code. All right, so first, the S-matrix rules for general mass and spin. And what's hard about this? Well, when we have massive particles, we also have a little group. The little group is SU2 in 3+1 dimensions. But how do we actually do it? We don't, just as for massless particles, we don't normally use objects that transform nicely under the little group, right? We use polarization vectors for spin 1 particles. And then we have to force them to satisfy that they're transverse. P mu epsilon mu is 0. Or let's say for spin 1/2, we use solutions of the Dirac equation. That's also a constrained object. It's a 4-component object that satisfies P / minus m u equals 0. The actual labels for an electron are 2, spin up or down, right? The actual labels for, okay. So what we want is to do exactly the same thing we did for massless particles, to just find the objects that transform nicely under the little group. Now, fortunately, in 4 dimensions, life is maximally simple because the massless little group is U1, and we've talked about it, and the massive little group is SU2, and SU2 is the easiest representation theory in the world. Irreps of SU2 are just symmetric tensors, and that's the way we should think about things. So instead of thinking, the point is that we can use the momentum of the particle to transform alpha to alpha dot indices, and because the little group is exactly the thing that leaves the mass invariant, if we transform to, let's say, all alpha indices or all alpha dot indices, we can just demand that the objects are symmetric tensors carrying those indices, and we're done. So, for instance, instead of saying we have a polarization vector, which is transverse, I just say I have this object, which is symmetric, and then I can use a P over M to take this to that, and that will automatically be transverse so long as that's symmetric. Okay, so that's how we label them. First of all, they're labeled by a symmetric tensor of SU2. And the formula is naturally chiral. That's good. The world is chiral. There's a very simple action of parity. And if you want to decompose the spins into particular basis, for example, we can always decompose the momentum as a sum of 2 pieces like this. Then the different helicity components, the different spin components are just projected out by contracting this tensor with some appropriate numbers of these lambdas and these etas. If you like the etas, specify the z direction. Okay, so now we know that the amplitudes are labeled by symmetric tensors for the massive guys, and just the usual lambdas and lambda tildes with the correct helicity weight for the massless ones. Now let's do the same thing we did before. We just go through one by one and write down all the 3 particle amplitudes. Okay, so here's the amplitude for 2 massless and 1 massive particle. And so all I have to remember, the only difference here is now this product is m squared. I have to just write down something that has the right number of indices. Downstairs, the only things I have available are the lambda of this particle, the lambda of that particle. I can write down some power of this to make up the helicity weights, and I'm done. Okay, so if I specify the helicities here and the spin here, there's a unique structure that I can write down. This makes it, for instance, things like Yang's theorem, that a spin 1 particle can't decay to 2 massless photons is trivial. It's trivial just because you can't, these numbers have got to be positive. Okay? And you also discover that a massive spin 1 particle can't decay to 2 gravitons, and a massive spin 3 particle can't decay to 2 gravitons, and so on. Okay? Now, this formula also makes it really easy to compute what the residues are when you exchange particles. That's the other headache if you try to do these things with polarization vectors, is that there are constrained objects. You have to take out traces, and that's where Legendre, Gegenbauer polynomials, and so on arise when you do these things concretely. Well, here it's trivial because you just match up the indices from one side to the other. So for instance, if I have just any general helicities on the outside, this is the residue that I'm supposed to get. And you may not recognize it, but in the case where these are all scalars, this is a way of writing the Legendre polynomials, and of course it generalizes trivially. All right, so that case is easy. Let's do the next one. This is the interesting one. 2 massive and 1 massless. And here what's going on is that, again, I have this 1 massless guy. I have to write down things that have downstairs alpha indices. Now what I can do is use the lambda for this guy, and I can use the momentum for 1 or 2 times a lambda tilde to get something also with a downstairs alpha index. Fortunately, these are equal and opposite to each other. So I have two two-dimensional vectors, u and v. And the overlap between them is m1 squared minus m2 squared. So there's two different cases. One is if the masses are unequal, then these two vectors just give a basis. And so I can expand I can expand every possible 3-particle amplitude in a basis of some number of u's and some number of v's, and the total number of u's and v's is fixed by the helicity weights of the particles. So there's, if you have spin s, for example, there's 2s plus 1 structures that you're allowed to have, and this is what they all are. These, roughly speaking, in a Lagrangian correspond to all the kind of magnetic moment type couplings you can have linking different particles to each other. The interesting case is when the masses are equal. If the masses are equal, then these are not a basis. UV is 0. And so if I want to write all possible tensors down here, I can choose lambda, I can use the epsilon symbol. But there's one other object, which is there's a little bit more information in this P1 lambda tilde. This vector is proportional to u because this inner product is 0. They're in the same direction. So the constant of proportionality is another variable that things can depend on, that the amplitude can depend on, and this is carries helicity weight. And once again, if I have equal mass particles, whatever they are, again there's 2s plus 1 structures, again there's just a bunch of epsilons, some number of these lambdas, and then a power of x to make the helicity weights work out. What's important about this is that this object x is not local. There's no, if you try to compute x in terms of the momenta, you will find that there's dependence on reference spinners, and it's not local. There's poles downstairs. Okay. Just to give a simple example, let's say we want to see what minimal coupling looks like, okay, in this language. We are not running on a Lagrangian, so what does minimal coupling look like? Well, all we do is we have to ask what combination of these couplings have the property that when I go to the high energy limit, the massless limit, I recover the massless 3-particle amplitudes with the lowest dimension couplings. And if I do that, it's something very, very simple. For example, for plus helicity, it's just x times a bunch of epsilons. If it's spin 1, I multiply by that factor. If it's spin 2, and anyway, the parity conjugate of that for the other coupling. All right. Finally, 3 massive is trivial, and I won't talk about it. Okay. So then now we have the same challenge as before. Given a spectrum of masses and spins and couplings, we want to be able to find a 4-particle amplitude that factorizes correctly. And again, as we said before, most naively, you would just take the 3-particle amplitude, you'd compute the residue, multiply by the pole, and sum over the different channels. And most of the time that works. And just to give you an example that might seem naively scary, but is completely trivial, let's say you're interested, there's the top quark and a photon, and there's some spin 3/2 excitation of the top quark, and you want the amplitude for photon top to graviton back top through this crappy guy, right? And you know, you might think, oh my God, you have to open up the Rita Schwinger paper and it's going to be a nightmare. But you just write down the answer, okay? Because this works. There's nothing wrong. These the product of these 3-point things gives you something totally local. You multiply it by 1 over s minus m squared. There's 2 possible couplings you can have on one end. And that's the most general thing that you can have, plus possible contact terms. So the only challenge, actually, is when we have the situation where there's a massless particle and 2 particles of equal mass, which of course is always there because we have electrons flying around or normal particles flying around, and that's because of this x guy. The x is not local. And so just as we saw for the purely massless case, when we try to do this thing where we jam the residue together and see what it looks like, we'll find that it's not local. It has a pole in another channel, and it's not obvious that you can make something work. Okay, now, but you can make it work, it turns out. And so we have an explicit expression for all 4-point tree amplitudes. You just give me the 3-point coupling, you just write down the answer for all 4-point tree amplitudes for any masses and spins without ever mentioning a Lagrangian. So that's the answer to Natti's question. So we can talk, at least for these production processes, we don't need to go back to a Lagrangian. We just write down what the answer is ahead of time, the most general answer. And of course, we can now start the machinery for doing this for all n. For example, we haven't done it, but I'm sure that you can add any number of massless particles that you want, and all the techniques using the recursion relations and so on will work. Things will start getting interesting if you try to increase the number of massive particles, and it'll be interesting to see what it actually looks like. But let me just give you some examples of what things look like when you compute in this formalism. Let's do something simple like Compton scattering. 2 scalars scattering against 2 photons. So that's what the Compton amplitude is for spin 0, spin 1/2, and spin 1. Okay? And you'll notice there's no gamma matrices here, there's no U bars and V's, nothing, right? We're just writing down the answer directly in terms of the actual. These are the tensors, right? So if you want a particular spin component, you just project these S's in the direction of the spin axis that you're interested in. Okay, and this S is a nice simple expression. Now you'll notice this A has some helicity weight that makes up for the weights of particles 2 and 3. And as I go from 0 to 1/2 to 1, it drops. I go from A squared to A to nothing. So this is for photon W scattering. Now you can ask what happens if you go to spin 3/2. This is interesting because we know that massless spin 3/2 particles, there's a problem. We're not allowed to have them. Obviously, we have to be able to have massive spin 3/2 particles, bound states, any kind of crap out there. There's all kinds of massive higher spin particles. And this formalism is giving you the answer for the scattering amplitude for off bound states, off anything you want, in principle, at least parametrizing it correctly. But you should expect that something changes. And if you just turn the crank, look at our general expression, indeed it changes. So the structure starts looking different, starting at spin 3/2. I don't expect you to look at it in any detail, but there's a very simple general conclusion that massive higher spin particles can't be point-like. And that just follows from general grounds, and that's because if you put in, for example, minimal coupling, the thing that you would naively make even the 3-particle amplitude look point-like at high energy, and now you calculate what the 2-to-2 scattering amplitude is, you find that despite your best efforts to say the coupling was dimensionless here, small dimensionless coupling, that the high energy limit acquires this extra factor of energy squared over m squared to the power of 2s minus 2. So it blows up for energies much larger than the mass. Okay? And of course, that's what obstructs taking the m goes to 0 limit. So that means that if you see a particle of spin 3/2, a charged particle of spin 3/2, it has to be an extended object. That this is the direct physical meaning that it has to be an extended object. Of course, every such example that we know, either they're ordinary bound states and they're extended objects, or they're strings, or they're something else. But of course, that's all true. All right, so that's all I wanted to say about this, and I think I have 5 minutes, so I'll have to be even more impressionistic about this than I want it to be. But let me just say a little bit about it. So this is now in the opposite extreme. So we're not exploiting these principles, but we're trying to see the amplitudes as the answer to a different mathematical question, and then try to see whether we can understand where the singularity properties come from that allow it to get a local and unitary interpretation. This is something that been working on for a long time was the picture that somehow the amplitudes, if you specify the external data, these z's are momentum twistor variables that are the best ways of talking about the momenta for external states in n equals 4 super Yang-Mills, that this is somehow the volume of a region that lives not in space-time, not in Hilbert space, some other projective space. So there is a concrete implementation of this idea where indeed, if you specify the external data, roughly the momenta and the helicities of the particles, there's a notion of volume that you can associate to some shape in this space, and that volume calculates the scattering amplitude. So many of you may have seen aspects of this story before. I won't go through this in any detail other than to just roughly say that it's a simple shape, it's a simple object, and a simple object that's roughly speaking the generalization of the notion of a simplex. So you start with something like the inside of a triangle, and you generalize the notion of the inside of a triangle in a number of ways. You generalize the inside of a triangle from projective space into the Grassmannian. You generalize a triangle from a triangle to a polygon. You then generalize that into the Grassmannian in the same way as you generalize triangles, and that leads you into the world of these objects. And the boundaries of this space have the properties that as you go there, the geometry really splits in exactly the same way amplitudes do. And the infinite dimensional symmetry of n equals 4 super Yang-Mills is very obvious. There's just the diffeomorphisms that move the points on the inside the amplitude around without changing what the boundaries look like. But the only reason I'm saying all of this is to remind you this has something to do with the notion of the inside. You're trying to take the notion of the inside of a space and generalize it. And that's something that I think we now have a deeper understanding of. So one way of asking the question is, can we give a more invariant characterization of what it means to be inside something? So let me just go back for a moment. See, if you're talking about being on the inside of a polygon, one way of specifying it is to say that the points are on the inside if they're a positive weighted sum of all the things on the vertices. That's one way of talking about it. So you say that this point is a positive combination of the external data. But this is a very redundant way of talking about things, right? If I give you a point, it's hard to check whether it satisfies this property or not. So if you want an effective way of checking it, if you want a more invariant way of checking it, of course here we know what to do. The inside of the polygon is also cut out by a bunch of inequalities. You have to be on the right side of this line, the right side of that line, the right side of that line, and so on. And so if someone hands you a point, you can check. In other words, if you have the face-centered rather than vertex-centered way of thinking about what the polygon is, you have an effective way of checking what it means to be on the inside or the outside. So with Hugh, we'd been working for quite a while to try to find the analog of this face-centered way of thinking about things. And there is an analog. It involves topological ideas as well as just being on the right side of boundaries. But it turns out there's an even more primitive understanding what it means to be on the inside. And it's this more primitive thing I just want to sketch for you to give you a flavor of the kind of thing which is going on. So, but anyway, this is the question again. I have some external data that lives in some k plus m dimensional space. K and m are related to amplitudes in some way, but for this purpose, never mind. But it's some k plane that lives in this k plus m dimensional space, and we want to know when is a k plane in the amplitahedron. So the idea is that we're actually going to take this high dimensional space and we're going to get rid of this plane by projecting through it. So we're going to quotient out by everything in that plane. So that'll take us from a k plus m dimensional picture to an m dimensional picture, and we can ask what that picture looks like. So, saying it again, if you've suffered through any of my talks on this subject over the last number of years, I always start by drawing the stupid picture of a triangle and saying that it's important that we're on the inside. And part of the difficulty, what obstructed us from seeing the right way of thinking about it, is that that was too complicated. We had to start with a simpler example, not the inside of a triangle, but the inside of an interval. Okay? So let's now talk about what it means to be on the inside of an interval. And here we see there's another way of talking about what it means to be on the inside of an interval. The y is on the inside of an interval if you jump from 1 to 2, you pass over y once. Okay. You see, that generalizes to if a point is on the inside of a convex polygon. A point is on the inside of the convex polygon if you project through now one of the vertices in y, the resulting picture, which would look like 2, 3, 4, you jump over y once. And you see, no matter who you project through, you always jump over y precisely once. Okay. So we can generalize that notion. We can say, imagine we have these k planes in k plus m dimensions. I'm going to project through y to get an m-dimensional picture. Let's do the simplest case, m equals 1, the very simplest amplituhedron. And what is a picture supposed to look like? Well, the only thing that's left is k, and the idea is that you're in the m equals 1 amplituhedron if you jump over y k times. Okay. So in other words, if you look at this series of overlaps between y, everything sort of tensored together with contracted with epsilons, but this series of numbers has to have the sign pattern plus, plus, minus, minus, plus, 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 with precisely k sign flips. Okay, and now how do we define the amplituhedron for general m? In physics we care about m equals 4, but how do we define it for a general m? Well, all we have to do is project to get to m equals 1. And demand that every possible way that we project to get to m equals 1, we get the same answer. We always get the same pattern of sign flips. Always precisely k sign flips, no matter how we do the projection. And so this is, okay, well, I won't have time to explain any of this. But it really is specified in binary. If you have the general geometry is we have, if at L loops, we have L, actually k plus 2 planes. They all intersect on a common k plane. And this series of numbers has to have precisely k plus k sign flips and k plus 2 sign flips. All right. And I unfortunately don't have time, but you could really do a concrete example to really compute an amplitude in this way. Okay, so you look at, if you want to calculate the one loop MHV amplitude, you just write down all possible such sign flips. In this case, it has to have, this series has got to have 2 sign flips, so it's specified by where the flips happen. It's some I and some j. And you then, there's a prescription for attaching a form with this geometry, which is nailed by the geometry. So it's all about where the sign flip takes place, and so you can really compute an amplitude in this way. All right, I don't have time to talk about this. The final, very quick comment I'll make is that in our picture of the amplituhedron to date, supersymmetry has been bosonized. So there's no, it's not supergeometry, it's ordinary geometry. And then there was some interesting way of converting the bosonic geometry to supergeometry. In fact, it turns out that it's even simpler than we realize, and the story doesn't really have these y's in it. So everything that I was telling you about, they're all, of course, sitting there behind the scenes, but I can specify what the structure is directly on the following very simple space. I just have the space of external data. These are these momentum twistor variables. They're in R4. Loops are 2 planes in this space. These are roughly twistors and lines in twistor space that correspond to points in space-time that are the loop integration variables. And so I have a configuration space that depends on endpoints, L2 planes in R4. On this configuration space, there turned out to be a canonical form of degree 4 times k plus L. This form is completely determined by having logarithmic singularities on the boundaries of the region specified by this binary code. What I mean is, as you move these z's and points around, you have to have the property that as you do these projections, you always have the same patterns of sign flips, no matter how you do it, no matter how you do the projection. And that determines what the form looks like. So this is just a differential form. You've never heard of supersymmetry. But now there's a very natural Grassmann object in town, dz. If you just take dz and you interpret it as the eta that appears in superamplitudes, this is the superamplitude. Okay? So this is a way of going from bosonic Grassmannian geometry to supersymmetry, Yangians, and so on. But it's all bosonic. All right, so let me just end. At least in this example, for planar n equals 4 super Yang Mills, we do have a concrete example where we see locality and unitarity as derived notions, very much joined at the hip, ultimately arising from these algebraic geometric combinatorial origins, really counting pluses and minuses. If I had another 20 minutes, I could actually prove locality and unitarity by looking at the pattern of these sign flips and seeing how they imply the factorizations that you need. So there's a couple of, I think, large open questions in this story. We've understood a lot about the singularity geometry of scattering forms, and we're also seeing the scattering forms as combinatorial geometry. We understand much little directly about the final amplitudes when you finish doing the loop integrations. There's this, the singularity geometry here should correspond to some intricate branch cut geometry. We don't understand that. And the analog of the question here, we're seeing these scattering forms are really determined by some combinatorial geometry. We have no idea. We have functions that are polylogarithms, elliptic functions, more complicated intricate functions here. What mathematical questions are the full n equals 4 amplitudes answering? I'll just mention this very briefly because there's an aspect that we're seeing everywhere here. There's a kind of cluster structure that's being seen all over the place, not only the amplitudes business and things that have nothing to do with amplitudes. I think sort of most remarkably to me, something that showed up in drawing these pictures of on-shell processes were equivalence relations on these diagrams that are sort of literally Seiberg duality for quiver gauge theories if you draw the duals of these diagrams and thinking of them as giving you n equals 1 quiver gauge theories. And I think the deepest question of all is really this one. I won't even talk about that, which is that there is an aspect of the physics here which I haven't talked about at all. We don't see n equals 4 super Yang-Mills, which is running, the RG. And I think that until, at least in my mind, until we get a good on-shell picture of how we're supposed to think about the RG, I won't be satisfied. In a sense, without the RG, we're running with the wind to our back at 200 miles an hour in this business because amplitudes aren't a very local question to begin with. So the fact that we managed to come up with a picture for what they are that doesn't have the interior of the space-time in it is maybe not so surprising. It's the RG, which is Euclidean, is off-shell, and the best way of thinking about it uses those notions as Wilson taught us. So if we could understand how to get that from this Lorentzian or maybe 2-2 point of view, that would be extremely interesting. The only hope I have along these lines is that the sort of structure of the famous Wilson-Polchinski equation for the renormalization group has, very striking, obvious, often remarked on formal similarities to the singularity structure of scattering amplitudes. All right, that's it. Happy birthday, Nati.
Thank you very much. Brief questions?
So I still don't get the answer to my question.
Yeah. The answer is maybe. But I mean, really in the narrow sense of what I was doing in that talk. In the narrow sense of what we're doing in the talk, we're just computing. We're saying instead of because all these things are done at tree level for colliders, right? And then you shower them, there's radiation and so on. But the hard part is all the tree process. And that's what you need. You need a Lagrangian for and blah, 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 blah. Now, of course, what we were doing was not this. What we were doing was indeed just phenomenological and saying, look, you don't actually need all that detailed information about what the matrix element looks like if you want to get the distributions that experimentalists measure at the LHC right. But your question was the correct, deeper question, can you actually do it without ever talking about the off-shell virtual particles? And the answer for those processes is absolutely. You can write all of them down.
And what about some strongly very interacting CFT, which
of course not. No. But that's precisely not what was being talked about in that meeting. We were talking about things like supersymmetry, things like simple things where you do use a Lagrangian anyway, right?
Can you elaborate on how you see Seiberg's duality, which is an infrared property, without having an RG?
Oh no, sorry. I don't see Seiberg duality at all. What I was saying is that in this, there are these pictures that show up all over the place, and there are cluster algebras. There are a series of objects on which you do simple moves, and you generate large algebras and collections of things, okay? Just very abstractly. Now, those cluster algebras show up everywhere. They show up in scattering amplitudes in the integrand. They show up in scattering amplitudes at strong coupling. They show up in wall crossing. They show up in totally different questions. They're not related to each other. They're not obviously related to each other. A very simple thing which doesn't have a lot of the extra structure on top of it is simply that you draw diagrams, these diagrams, bipartite diagrams with black and white vertices. Those correspond to certain on-shell processes for scattering amplitudes. And as a scattering amplitude question, there's many different ways of representing exactly the same function that are related by moves. Now, you take exactly the same picture with black and white vertices, you draw the dual graph. The black and white tells you to put arrows on the graph so you get a quiver. And now you think of it as an n=1 gauge theory. And Seiberg duality on that n=1 gauge theory is the same move that leaves which interpret as an amplitude, which leaves the amplitudes invariant. That's a small part of the fact that it's the same cluster structure which shows up over and over again. I think it's rather fascinating, this same cluster structure is showing up everywhere in completely unrelated things. I know Nati's attitude about this is, well, maybe he's not sure, but you say maybe it's like the Laplacian or something. There are things that show up everywhere with no, just because it's, there's not so many mathematical structures out there and they'll be used over and over again. My answer to that is that if these things end up being as important as the Laplacian, that would be pretty awesome. But it's also possible they're related to each other for deeper reasons. All of these things come down from the 2-0 theory in one way or the other. And
Okay.
Yeah, that's...
Okay. Let's thank Nima.
Good evening, ladies and gentlemen. I'm Robert Dijkgraaf, the Director and Leon Levy Professor at the Institute for Advanced Study, and it's a great pleasure to welcome you at this kind of sold-out event, a public talk that coincides with our semi-annual Board of Trustees meeting. It's a particular pleasure to welcome our trustees to this event. Just as a practical matter, we will have a lecture, and then at the end of it there will be a question and answer period. Now, our speaker today requires little introduction. It's Nima Akani Hamed, who is a professor, of course, in the School of Natural Sciences at our institute. And the title, you should already see it behind me, The Inevitability of Physical Laws, with the subtitle, Why the Higgs Has to Exist. Now, Nima was particularly firm on this because he kind of very publicly announced that he was willing to bet a year's salary if the Higgs boson would not be found. And one of the most pleasurable experiences of just the first few days of my tenure here was that on the very early morning of July the 4th, we had a very special fireworks because we had a champagne toast to the discovery of the Higgs particle, and actually that champagne was at the cost of somebody who had taken up that bet. And so I'm happy to report it was a high quality champagne that we drank. Nima is somebody who kind of expresses his kind of wonder and enthusiasm about physics in a quite unique and powerful way. Although both his parents were physicists, he described himself to be as an act of teenage rebellion to study physics anyhow. And so I think actually this is a very clever act of reverse psychology on the behalf of your parents. Thank you very much. You studied at the University of Toronto and earned your PhD in physics from the University of California in Berkeley in 1997. Nima worked as a postdoctoral fellow at the SLAC National Laboratories before becoming an assistant and an associate professor at Berkeley. In 2002 he moved to Harvard to become a full professor there, and he remained there until he joined our faculty of the Institute in 2008. There's an endless list of honors that Nima was awarded. I just mentioned the Sloan Fellowship, Packard, the Gribov Medal of the European Physical Society, and the Raymond and Beverly Sackler Prize. But I think in many ways this was kind of topped by a prize that was awarded at the end of July, when in that month we had another piece of excellent news, which is that Nima, along with 3 colleagues here at the School of Natural Sciences, was among the first winners of the Fundamental Physics Prize. And that's a remarkable recognition of groundbreaking contribution to theoretical physics, and it included a very generous award of $3 million to each of the laureates. And you might kind of wonder whether, Nima, you would still have bet your year's income if you would have known that. In fact, we are especially delighted that the creator of that prize, Dr. Yuri Milner, is here to kind of celebrate that. warm welcome to you. NIMA's work on particle physics and its connections to experiment is truly visionary. There's a long list of his achievements, but all of them, I think, stand out in terms of a very fresh and broad way of thinking, very unexpected way of thinking, and that has enormous traction both in the theoretical and in the experimental world. And he, for instance, has radical ideas that it could be very large in terms of physics speak, extra dimensions, completely revolutionized parts of theoretical physics. And he has also played a leading role in how these modern theories, what their implications are for the great and exciting experiments that are going on now at the Large Hadron Collider in Geneva. After the announcement was made of the discovery of the Higgs this summer, the New York Times quoted NIMA as saying, "It's a triumphant day for fundamental physics. Now some fun begins." And I think that fun is can't think of better hands to put that fun than in NIMA's, and I hope that you will join me in welcoming him here to the stage. NIMA Kahneman.
Well, it's a really tremendous pleasure to be giving this talk today. As you all know, the Higgs was discovered, politically correctly speaking, a Higgs-like particle was discovered at CERN back on July 4th, and there's been an endless slew of descriptions of what the Higgs is and what the associated ideas are in the popular press. And they all use one variety of metaphor or another to describe the physics. Now, there's a problem with talking about the Higgs that almost all these metaphors are just terrible, and they don't actually reflect what's really going on. But all of us, I've used these metaphors myself, so I'm not besmirching anyone else, but for the purposes of this talk, I decided that I would try to do something very dangerous, which is to try to explain what's actually going on. I take some inspiration from the spectacular talk Juan Maldacena gave here a number of weeks ago that I hope many of you were also at. Juan's talk was really precisely correct. He used analogies, but the analogies were not just random analogies. They were really precisely, in a very sharp sense, correct. And I'm using that as an inspiration here as well. The talks are going to be completely complementary. And in a few places, I will talk about what the sort of connections are between these two ways of thinking about things. One aspect of the story that I really want to highlight and emphasize, and it's a broader point than just the Higgs. We're going to use the Higgs as an illustration of this general point, is often when we talk about what's going on in physics, I think if you're not a professional physicist, you might get the sense that these are a group of people who are just pulling things out of thin air, left, right, and center, and somehow they describe nature sometimes. Maybe other times they don't. And, you know, whether they work or not work is dependent somehow on their sense of aesthetics, what's pretty, what's good, what's bad. But it seems perhaps very dependent on the people who are thinking of these ideas. And what's not, I think, commonly appreciated, which is what I really want to stress in this talk, is we understand so much about the way the world works that a lot of the broad outlines of what even possible candidate theories that could describe nature can look like are just forced on us. There's nothing we can do about them. There's no choices. There's no, 10,000 other ways things could go, and we're choosing some of them because we like them, because they're pretty. The way the world works is very, very largely constrained by the laws that we know already. There's an inevitability about the structure of the laws of nature, which is what I want to talk about. And a particular example of this kind of inevitability, this incredible power we have in our understanding of how things work, is going to lead us to why it was that so many of us, certainly not just me, many people would have been willing to bet years of salary that the Higgs had to exist. But why it is we knew. I mean, if you think about it, this is kind of amazing. There's this group of people, a few theoretical physicists wandering around the world, who knew when this experiment is done, this big experiment is done, this particular measurements are made, this thing must happen. We just knew that ahead of time, and it happened. So why were we so confident? Why are we so sure it had to happen? That's what I want to convey in this talk. So let's start just with a review of what we know about the world. So the most basic sense, we know there are things out there made out of matter. Matter is made out of atoms. And in atoms we have, so here's a hydrogen atom, we have an electron going around a proton. And if we take a peek inside the proton, we now understand that the proton is not actually a fundamental point-like particle. It's itself made out of other particles called quarks. So the proton is made of 2 up quarks and a down quark. A neutron, another constituent of the nucleus, is made of 2 down quarks and an up quark. And this matter is acted on by various kinds of interactions. We know there's 4 basic interactions, 2 of them that people knew about for a very, very long time, gravity and electromagnetism, and 2 that we discovered really at the very, very end of the 1800s and the early 1900s, which operated very short distances, the strong nuclear force. So inside a nucleus, for example, we can have 2 protons and two neutrons here. This is in a helium nucleus. And you might wonder why these protons manage to stay inside the nucleus. They want to repel each other by their electric repulsion. Well, early on, there was something that people imaginably called the strong force that kept them inside the nucleus. We now understand that this strong force is a residual of something else that we'll talk about a little more. And finally, there was something called the weak force, or the weak interaction, which is ultimately responsible for radioactivity. If you take a neutron out in empty space, it sits there for 15 minutes, and then it disintegrates. It disintegrates into a proton, an electron, and something called an anti-electron neutrino. Now, 15 minutes is a gargantuan timescale compared to all the various times of atomic physics and nuclear physics and so on. So that's why it was called the weak interaction. It had to be something incredibly feeble that had to take so long in order to do this. But this is ultimately what's responsible for radioactivity. And these interactions, acting on the matter that we know and other particles that we've discovered since, hold sway over an enormous range of distances, all the way from the size of the observable universe, around 10 to the 28 centimeters big, down to, as we go down to shorter and shorter distances, there's something exciting happening at almost every factor of 10, shorter and shorter distances. Galaxies are 1 million times smaller than the universe. The distance between the Earth and the Sun is like 10 to the 13 centimeters. People are like 1 meter big. Atoms, protons, and neutrons are around 10 to the minus 14 centimeters. Incredibly tiny, around 1 million times smaller than the atom itself. And finally, we go down to this very, very short distance scale we'll talk about a lot in the rest of the talk, around 10 to the minus 17 centimeters. It's called the weak scale. That happens to also be around the frontier of what we're probing with very, very high energy accelerators like the Large Hadron Collider. We're actually probing these very, very tiny distances. Now, a remarkable thing that we've discovered is that actually all of these things, this whole collection of stuff, the matter and the interactions, are described in a completely common way, in a completely common language. So if we start with the most familiar, familiar interactions, just the electromagnetism, like the electric repulsion between a pair of electrons, and gravitation, it turns out that both of these interactions are associated with a little stick figure like this. Electrons interact with a photon. Here they can interact with a graviton. The thing which interacts with the photon is actually the charge of the electron. The thing that interacts with the graviton is, well, in the Newtonian picture of the world, the force of gravity has to do with masses. The more and more massive an object is, the bigger and bigger gravitational force you have. But we now know, because of relativity, E equals mc squared. So really the thing which is the analog of charge for gravity is the energy or the momentum of the particle. So there's a charge associated with here, which is like the charge, which is the normal electric charge. And the analog of the charge when it interacts with gravity is energy and momentum. So there's some basic little stick figure interaction like this. And everything else which actually happens when we take electrons and photons and make them interact just comes from putting these pictures together. So if I want to have two electrons banging into each other, what's really going on is two of these basic building blocks and exchanging a photon there between them. So in a specific sense that I can't illustrate with these pictures, but which is really there precisely, there is some sense in which there's not a real photon, but what's called a virtual photon, something that's sort of quantum mechanically fluctuating out of the vacuum, which is what's giving rise to this force between two electrons. And you can see the force between two electrons gets weaker and weaker as you go to larger and larger distances. That tells you something. It tells you that the size of these quantum mechanical fluctuations is weaker and weaker at larger and larger distances. It's stronger and stronger at shorter and shorter distances. And that's a sort of a basic consequence of the Heisenberg uncertainty principle. But anyway, that's the picture we now have for the simple fact that two electrons can, for example, scatter against each other just by repelling each other by their charges. And you can put these together to make all sorts of complicated processes. So all sorts of complicated things happening in the world, in the end, just come from gluing together these basic little elementary interactions. Now, the strong and the weak forces don't look like that at all on the face of it. They look completely different than the electromagnetic force and the gravitational force. But the amazing thing that we learned in the second half of the 20th century is that, in fact, all of these forces are described fundamentally in exactly the same way. That if you go to short distances, you discover that what's really giving rise to the strong force is exactly the same kind of stick figure. Instead of having electrons interacting with photons, we have quarks interacting with something called gluons. So this is what's responsible for the strong force. The weak interactions are associated with, instead of having two electrons interact with a photon, we can have an electron and a neutrino interact with something called the W boson. Looks just like the photon. All the pictures look exactly the same. There are little detail, there's some few detailed differences. Here, for example, so far in all the pictures, it was the same kind of thing. Quark, 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 electron, electron. Here we get something a little new. We have an electron and a neutrino. But it's not really fundamentally different. For the quarks, so these are the weak interactions now. We can have an up and a down interacting with this thing called the W boson. And it turns out they have a cousin called the Z boson that does just connect, for example, an electron, and a Z. So fundamentally, at short distances, they look identical, essentially identical. So why did we think they looked so different? Why did we know about gravity and electromagnetism for centuries and centuries and only found out about these other guys like 100 years ago, 110 years ago? And the reason is that the apparent enormous disparity between these forces is a kind of a long-distance illusion. For example, let's talk about the strong interactions. So we have the quarks interacting with these gluons. Now, we have electrons and photons. We've seen electrons and photons out there in everyday life. How come we haven't seen the quarks and the gluons out there in everyday life? It turns out to be a detailed effect. It's a very important detailed effect. It's a detailed effect that earned some people the Nobel Prize back in the 2000s. But it's really a detailed effect that because of some subtle quantum mechanical reasons, the force between the interaction strength between quarks and gluons gradually gets stronger as you go to longer and longer distances. Very, very gradually gets stronger. And eventually, at a long enough distance scale, it becomes so big that it traps the quarks and the gluons and everything else inside the protons and the neutrons. So we say that they're confined. This is at a very long distance scale. A long distance scale to a particle physicist is around 10 to the minus 14 centimeters, a million times smaller than the atom. Okay? But this is, to us, is a gargantuan, very, very big distance scale. Okay? But this is a detail. It's a very important detail, but it's a detail. Fundamentally, it's the same thing. Fundamentally, we have these same basic stick figure interactions. What about the weak interactions? Well, the reason why it took so long to discover the weak interactions, the reason they're so weak is even simpler. The photon is a massless particle. Because it's a massless particle, it doesn't cost as we go to longer and longer distances, it's sort of possible to get longer and longer wavelength excitations of the photon that have lower and lower energy. And so no matter how long distances you go to, you get some force from it, some reasonable size force from it. Granted, it gets weaker as we go to long distances, but it's still visible, and we talk about it. It's a famous inverse square law. The difference is just that the W particle is massive. It's not massless, it's massive. And because it's massive, it really costs an enormous amount to excite it out of the vacuum. So the range of this weak interaction is very short range. The W boson is so massive that the effective range of this interaction is something like 10 to the minus 16 centimeters or so, which is 100 times smaller even than the atomic nucleus. But again, it's a detail. If we go to short enough distances, everything starts looking similar. This is the real reason we want to build high-energy accelerators and go to short distances in our part of physics. It's not so much because often when people talk about this, they talk about wanting to understand what the building blocks of all matter are and things like that. Maybe that's what some people care about. It's not so much what I care about. I think it's not a lot what many of my colleagues care about. After all, understanding all the different building blocks of matter sounds something like chemistry, and I kind of flunked chemistry a number of times, so it wouldn't thrill me to be doing something like chemistry. No, that's not why we actually do it. We go to short distances because we've learned in this way. We've learned that the essential unity, simplicity of the laws of nature become manifest. They're hidden at large distances by a variety of accidents. But when we go to short distances, we finally see them. This is a really extraordinary fact that we see for the first time all these different interactions described in a common way, a common language, just one set of stick figures describing everything. It's pretty amazing. And we discovered that by going to short distances. So it pays to go to short distances because then you see what's really going on with the fundamental laws of nature unvarnished, not hidden by these relative accidents. It took us 2,000 years to go to distances short enough to see that all this was true, but then we see it's true. We've learned something really profound about the way the world works. Okay, so now, for a lot of the rest of the talk, maybe I should have said this at the start. This is not the most conventional description of the Higgs and all of this physics. And it might require a little bit more audience engagement. So we're going to be thinking and counting on our fingers a lot. Okay? So, but we're going to have to count a lot. Actually, one hand will probably suffice. Yeah, one hand will suffice, okay? But you're going to see these numbers floating around. 1/2, 1, 3/2, 2, 0, and so on. So just be forewarned that we're going to see a bunch of numbers floating around. Okay. All right, now, there's a really important property that particles have. It's actually one of their defining properties. It's one of the things that labels what a particle is. Particles have something called a spin. So you can think of an electron very loosely as like, has some charge, and it's spinning around. It intrinsically has some spin. It can spin in some direction. Now, so there's some angular momentum that's associated with that